Okay, so we're going to look at some collision problem examples, and the first one is a totally inelastic collision, so it's one where they stick together. We have a 98 kilogram fullback running along at 8.6 meters per second when a 76 kilogram defensive back running in the same direction at 9.8 meters per second jumps on his back. What's the post-collision speed of the two players after the collision? All right, so the first thing, as always, we're going to write everything down and make a sketch. So we have mass 1 is 98 kilograms, and velocity 1 is 8.6 meters per second. Mass 2 is 76 kilograms. Velocity 2 is 9.8 meters per second, and since he jumps on his back, they're moving in the same direction. So if we picture the situation with like a simple sketch, we have 98 kilograms moving at 8.6 meters per second, and the other person is moving in the same direction faster, so at 9.8 meters per second and 76 kilograms. And after the collision, they move as a unit at some speed, which we want to know. This is the 76 and this is the 98, just a basic sketch. Okay, so what we have to remember is that total momentum before equals total momentum after in any collision, and we also need to remember that momentum is mass times velocity. So I'm going to set up P initial and P final. I have object 1, I have object 2, and I have the total. So I make myself a chart. Okay, now for the first object, it's 98 kilograms times 8.6 meters per second. So if I put that in the calculator, I get 842.8. And for the second object, I have 76 kilograms times 9.8 meters per second. So that gives me 76 times 9.8 is 744.8. So to get the total momentum, I'm going to add the two of these together. So this plus 842.8 gives me a total of 1587.6. And the units up here are going to be kilogram meters per second. Same thing here, kilogram meters per second for the momentum. Okay, now after the collision, I know the total momentum has to be the same, so we have 1587.6. This is equal. Now, each person is moving at the same speed because they're stuck together. One's on the other person's back. So we have the 98 kilogram person moving at some unknown speed v, and we have the 76 kilogram person moving at the same unknown speed v. So if we look at this right-hand column, what we have is 98v plus 76v equals 1587.6, because this gave me 98v and this gave me 76v. Okay, so 98 plus 76 is 174v equals 1587.6. I'm going to divide both sides by 174, and I get V is equal to, let's say, 1587.6 divided by 174 is 9.12 meters per second. So that's the answer. Now, I'll also go over in this first example how we check our work. So we can do it in third column, we call it change in momentum, delta P. So what we want to do is we want to look at the final momentum minus the initial momentum. The final momentum of the 98 kilogram person is 98 times V, and V is 9.12. So that number, 98 times 9.12, is 893.76. I'm going to write it in the box over here. And the 76V gives me 693.12. Now, I can subtract the final minus the initial momentum to get the change in momentum. So 893.6 minus 842.8 is 50.8 for this one. And 693.12 minus 744.8 gives me negative 51.7. So my change of momentum is almost zero. It's approximately zero. The reason it didn't come out exactly is because I rounded my answers a little bit as I went through here. You can see that they're very close to the same. It should turn out that when you get delta P for each object and add them together, it should come out to approximately zero every time. Okay, in the next